Okay, great. So you've heard about some of the exciting things that are happening in quantum computing and quantum science in general. And at Mason, we have put together a new master's program in quantum information science and engineering. And so, as again, you've already heard, right, companies are really already looking for workers in this new industry. It's an exciting area. It's growing in terms of employment and prospects into the future. And we're concentrating in this program on really trying to develop the skills that we know industry is looking for through surveys and other conversations that we've been having with them to identify those key areas. So basic knowledge in quantum is obviously part of that, but also things like communication skills, systems engineering skills, and teamwork and collaboration are all really critical things for industry and focuses of this program. So you've heard about quantum computing and how it's poised to revolutionize lots of different fields, but quantum encryption, quantum sensing, which is also part of what's going on at Mason, and quantum materials are all pieces of this new field as well. And so, why is it not letting me go? Oh, hold on, sorry. It ended up on the last slide, not the first one. That was the summary version. Apologies. Okay, so what does the program look like? This is a map of the anticipated path through the program. It's 30 credits total. And so the courses include some of the core physics courses and quantum computation. The center is an internship or externship experience, as well as some of these electives. We'll talk about those in a little bit more detail here. So the core physics courses that are part of this is a concentration within our physics master's program. So it is an MS in Applied Engineering Physics. Those core physics courses are actually available at 2 different levels depending on background. So if you're coming out of chemistry or engineering or mathematics, those are available at an upper level, it's the upper level undergraduate, graduate type courses to get you up to speed on those physics courses. This quantum computation and quantum information is one of the core pieces of this program, and Ming will talk more about that in just a minute when I am done. So I'll leave some of the discussion of that course to her. And here are some of the details, but since she is here, I will let her discuss this course. And then we have Systems for Quantum Scientists. This is one of the new courses that we're developing and has been approved and will be offered for the first time, possibly spring 22, which would line up with even the next year of teaching this program. And it's really designed to prepare students for their industry experience, particularly with regard to sort of hands-on problem solving, wide range of tasks, thinking about timelines and budgets, and how you do this as a team. This comes out of lots of discussions that we had with people in industry and what they're really looking for as they hire in this field. As I mentioned, sort of central to this master's program is an internship experience. We've been working with colleagues in industry to try to develop opportunities for students to do this. Research experiences at Mason and other universities or government labs are also possibilities. We've left that flexibility in the program depending on student interests and directions down the line. And then, so here's the Systems for Quantum Scientists. It's really this real world problem solving, requiring that students work together. These are, again, building some of those skills that industry has said are really central to what they need in the workplace, and will involve regular meetings to discuss aspects of the challenge that they've been provided and how they're going to solve it and what that proposal is going to look like. So they'll learn some of the principles of systems architecture. We're working with colleagues in systems engineering to develop this, create a research proposal for the project, and submit it in stages as it's developed with regard to solving this challenge, and ultimately pitched to faculty and experts at the end of the course. So then beyond this, the program includes a focus area elective, which are either part of the hardware or software track, as well as a handful of other electives that can be drawn more broadly from courses across sciences and engineering as appropriate to the degree program. So here are the hardware track courses, and this is something that is where it currently stands. We hope it will develop in coming years as we build more of these courses and sort of refine these tracks. So there are a whole range of hardware type courses, from solid state physics and instrumentation, this nanoelectronics and nanomaterials type courses, for students involved in that part of the hardware side of these things. Again, it's more around the materials for that track and some sensing, whereas the software is really about either cryptography for those interested in that direction, or some of this more computation oriented courses that are involved. So I will keep it brief because I think we were running short on time and stop there. In terms here, sort of just revisiting what I've said about why this is an exciting new area. We've really been building this program to provide opportunities for students interested in it. We'll be refining the sort of focus areas, I think, in the coming years, but those are available as well. And I will stop there. So I'm.
Thank you, Jessica.
Yeah.
If you have any questions, you can ask now or put it in chat. Yeah, I have a pre-collected question from Vilas Mandalekar from World Bank Group. Vilas, you can, if you're here, please talk.
Likewise here.
Vilas, you can unmute yourself.
Yeah.
And,
great.
Yeah.
The question is regarding this quantum computing courses being offered at the undergraduate level. Since this is a paradigm shift from the classical way of computing, there is no reason why it should be done after you have done a computer science undergraduate and then take this on, which you have to unlearn a lot of things that you have learned in computer science the classical way. So the question is, why is there not a course or something to start this off at the undergraduate level, so that students of future are not burdened by the computer science baggage that they carry, perhaps?
Yeah, well, Ming is going to talk about this course in just a minute, but it is actually available at both the undergraduate and graduate levels. So there are currently undergraduate students taking it, getting introduced to quantum computing as part of it. So very much, I was focusing on discussing our new program, which is at the master's level, but we're starting to develop and implement some of these at the undergraduate level as well, because you're absolutely right. They need to get involved in quantum computing and quantum science and see where it's going into the future.
Thank you.
Just add in, you can start even before getting to university. I think later on in like half an hour, you would hear another talk from one of the presenter who I think started this work as a high school student. And the work is pretty cool. Keep an eye on that.
Okay.
Anything else?
I guess it's probably the time we switch to me. So if you have any questions, I think we can discuss in chat, continue the discussion in chat, or we can move to the Gather Town Q&A room number 2. You can still stay in Zoom, as I said, but just log into Gather Town and the chat over there. Thank you. Ming, if you're ready, please start.
I still cannot share. I think Jessica has
to stop.
Okay. All right. Here, let me try to share it. Okay, now run the slideshow. Okay, hopefully you guys can see it now. And all right. So I will just use a few minutes to talk about a little bit detail about this class, since there are some questions about it. And also I would like to introduce to the next three presentations will be given by our students get involved in research and education program. So first of all, the class that is the course we offer at Mason. This actually is the first undergraduate level class on this subject I've offered at Mason. We started 3 years ago, and this year it's offered every fall semester. This will be the fourth year we have this class. We run it on campus face-to-face, and we also run it on Zoom. So we have experience in both areas. And unfortunately, we still have to run it on Zoom this fall. And it's going to be, you can see the meeting time, it's here. This is going to be the lecture on Zoom at that time. And we're going to post the lecture notes and recording on Blackboard, and the homework communication was through Blackboard. So hopefully, this will offer some flexibility for people who wants to take it but cannot come to campus. If you want to take the class for credits, you could do physics at both undergrads and grads level, and you could do math as well. It's co-listed. So if you are interested to take those and talk to your coordinators, your program coordinators, and see which are the best fits into your needs. And by the way, this is my email address. If you have any questions, just shoot me email. And also, this is a textbook we're going to use. You can Google it up and have a preview and see if that's something you're interested in. And for the prerequisite, we listed linear algebra and university physics. But in reality, we don't need the whole linear algebra book, as long as you are familiar with vector space operators, and you're not afraid of multiply two small matrix together, then you're ready to go. And you don't need to know quantum mechanics at all. So we have the majority of students in our class in the past, undergrad students, and pretty much every level. You can join us even in your freshman year. And we have the students from EE, from CS, from math as well. All right, so that is about the class. And an important component in the class is the we're going to use hands-on projects. We're going to use the IBM platform. So those are you see the picture of the quantum computer, and this is the image that you have the 3 qubits actually is in here and connected in a lattice, and those are the chips. Actually, those are actual qubits sitting on those plates, and you have all those wires connection to do the control. Right, those are the hardware, and this is the example of all the qubits, how the qubits are connected to each other on the chips. And we're going to focus on this part in this class, and we're going to use their software package and write a Python-based code and to access those the hardware online, so you can actually play on those computers. And you see this type of quantum circuits before in the previous talk, and we're going to do a lot of this. We're going to analyze step by step what happens to those qubits that on the horizontal line. So you have a few qubits in here, and you have a single quantum gates, and you have a 2 qubit gates. So basically, these are the basic toolbox we can use to build quantum circuits to run quantum algorithms. So to solve some problems. Actually, we use this platform to in our research as well, in our research project as well. So that leads us to the next slides. Those are the 3 talks you're going to hear right after this. The first talk will be given by Jacob and Connor. Both are in our undergrad program in physics and math. Both of them took my class last year, the quantum computing class. And they're going to talk about this project supported by a NSF grants. The goal of this project is to find optimal synthesized algorithm for few qubits. And we're working on 2 qubits right now. The goal is to find the best algorithm that will require the least amount of resources, that's the overhead, to do the quantum error correction down the road. And the second talk will be given by Javier. He is in the graduate program in the CS department. This is the project supported by the QSEC seed funds last year, and we have another one coming this year as well. So he's going to talk about the estimation of overlap of quantum states. So basically, you want to find the similarity or the difference between 2 quantum states. And the goal for his project, or this project we're working on, is to how to handle the overlap estimation for a large number of states at once. And there is a lot of applications in this area. You're going to talk more details from his talk. And also I want to introduce you the people co-directing those projects with me. Maria, you heard his talk, and Michael and Andrew, they're affiliated to Math Department, GMU, and also they're both from Booz Allen Hamilton. If you have questions, you can talk to them as well. And also the last talk, actually Ian Morris is, he's graduating from our program, physics program, and moving on to grad school this year. And he got involved in both research projects, but he's going to talk about the QSEC, how to use QSEC. He actually learned QSEC on his own through a direct reading, a senior project with us. So this is another way you can learn the material. If you don't want to take the class in the previous slides, and you can learn this on your own pace and still earn credits towards your grade. So that is I'm about to say, and without any further ado, I can give the room to our next presenters, Jacob and Connor, or you have